Okay, a little quick summary. We have some object rotating about a point, an axis, and the r vector is distance from the axis, or the vector from the axis to the point of application of the force. Now this could also be, vector from the axis to any point along the line of application of the force, and it would still give us the same result. We change the r vector, change the angle if we went to a different point on that line, but we'd still end up with the same result. And we'll make that more plausible later, or make that very clear. However, it's worth keeping in mind right now. Okay, so we just do the r cross the f. The r cross f vector is out of the board, perpendicular to the board, perpendicular to the plane of rotation. And being the torque being a counterclockwise torque, we have a positive vector. If we have a x, y, z axis, let's say the z axis coming out of the board, and we have an x and a y axis in the board, a positive r along the x, a positive f along the y, by the right-hand rule, will give us a positive r cross f in the z direction. And as I think I mentioned before, we do need to come out of the plane to get one single direction to represent the torque, or the, as far as that's concerned, the angular velocity or the angular acceleration. Okay, well, we get then torque is r cross f. I think I've mentioned that maybe not, at least on the videos, that the units are meters times newtons, which gives you the same thing as newtons times meters, but it's not joules. In this case, it's torque. And we usually, we tend by convention to write that meter newtons, okay, as opposed to newton meters, so we don't accidentally switch it over and think that we've got joules. And that can be a little bit confusing, so you want to be careful of that. The work done is just your torque dotted with your delta theta vector. And the net torque is your moment of inertia times your angular acceleration vector. So these are all completely analogous. Torque is analogous to force. Torque times angular displacement is analogous then to force times linear displacement, and gives you work. And tau net equals I alpha. Well, this is what gives you an angular acceleration. It's analogous to a force, and I is analogous to a mass, and your alpha is then analogous to linear acceleration. The units are slightly different, and the quantities have different meanings, but it's very much analogous. So your intuition in working with forces and accelerations and motion in linear applications, objects moving in a straight line, comes over very nicely to the situation where we're accelerating angular bodies. Moment of inertia is the sum of the mi/ri squareds, as we've talked about. Okay, the sum of the masses times the squares of their distance from the axis of rotation. And we could say that's the sum of delta sub I, where delta sub I is the average density of a volume unit times the volume unit times the, again, Ri squared, the distance of that volume unit squared, distance of volume unit from the axis of rotation squared. And that leads us in a limiting process to the integral of delta r squared dv. Now we'll talk more about this type of an integral, but that's how we integrate to get a moment of inertia. I'll have to do some examples of that.